Huh?
You want chocolate color?
Yeah, I found it. Yeah. Mhm. And yellow and blue. Okay. Just to wake you up, I want to say a few preliminary words. You probably already know, but if someone don't, most of great discoveries are made by PhD students like you. Okay, that's a secret which usually professors try to keep. But so what I'm going to tell you now at the beginning was something which one PhD student uh, stopped some professor at the corridor, which was not his professors. So his advisor gave him a problem which he did not want to solve, so he thought about other things, and then he had some thoughts, but he needed permission to write his thesis on this and not on what he was given by his advisor. So he met the student. His name was Leo Szilard. He was a Hungarian. It was 100 years ago about in Berlin. And so he met in the corridor younger professor who told him that, I have some ideas. What do you think? What would make a thesis? And professor, who was Albert Einstein, young professor at the time, just came from Prague to Berlin, and he listened for 5 minutes and said, well, that's nonsense. And then Leo asked for another 5 minutes. And in this conversation, the first time the word bit was mentioned, which is the abbreviation of binary digits. So if you want to know where this bit started, from which we're all now using, it is in this conversation in the corridor of Berlin University. And after another 5 minutes, Einstein said, yeah, I'll talk to your advisor, who was Max von Laue, very famous Nobel laureate. I'll talk to your advisor and convince him that you can write your thesis on this and not on that. Okay? That's the official beginning of information theory. Of course, then you can go back, as I told you, and read Maxwell's diary and understand that Maxwell actually understood most of it. Because what Szilard thought, he thought about Maxwell demon, etc. Okay? So that's, okay, now it's time, so now let's start lecture and not fairy tales. So what I'm now officially starting information theory, which means we'll be writing basically the same formulas, but we'll be saying the different words. Okay? So we'll start from a formal situation. So there are n boxes. And in one of these boxes is a candy. You want to get this candy, and you ask the question, where is my candy? And somebody tells you, in the box number 15. Wow, you got a candy. How much information you receive? Okay? So that's a formal question, which people started to ask about 100 years ago, before Shannon. Shannon was still at high school, where people were asking this. And apparently, let's call this information I must be a function of n, right? Because if n equal to 1, it must be 0. So we do know that I of 0, I of 1 is 0. Okay. We would expect it to be a monotonically growing function of n, right? The answer 1 out of 2 and 1 out of 22 bring you the same candy, but not the same amount of information. Like already was yesterday, mentioned that information must be somehow proportional to the degree of surprise, or, as Shannon 20 years later would say, to your prior degree of uncertainty. Okay? Also, you would expect this information to be additive when you multiply. Let me explain what I'm saying. Imagine that every box had also m compartments, okay? And you ask the question, in which compartment is my candy? And each box is the same. So now you have n times m compartments, but you can obtain this information in two steps. First, you ask in which box, you get the answer, and then you ask in which compartment inside this box, you get your answer, okay? What you immediately conclude, what is this function? It's a log. Incidentally, you know why people invented logarithms? Who did it, by the way? Napier. Why would people lived for happily 3,000 years? I mean, Indian civilization did great mathematics, but did not need logarithms. Why would Brits invent logarithms? Any idea? Huh? Because multiplying is difficult and adding is easy, right? So they created these tables. You need to multiply two numbers, right? You look at the table, there are logarithms. You add their logarithms and then look at inverse table and get your product, okay? That's because, okay, so now we say that this must be a logarithm of n. And incidentally, for every logarithm, you ask what would be the base over here. And uniformly in this course, I will be using base 2, well, following Leo Szilard, because I will be asking questions which would be separating into two. For example, I have n boxes. My first question is, which half, right or left? Then second question in the remaining, which right or left? So how many such questions I need? This number, right? So if you want to take, if every time you're asking questions, so every answer to such questions brings 1 bit, and this is the number of bits, okay? That's an essential idea. And then you say, well, come on, but we usually get information by words, right? For example, you get love. How much information it brings?
So where is the m in this log function? So there is no n, as we were needing two n and m's earlier. Earlier we were needing two n and m parameters, but when you rewrite it as a function of log, then there is just m. So can you please explain?
I don't understand your question at all.
So in the first equation, we have I information n plus information m in the first equation, and then
No, this is a function of a single variable, okay? This is a function of a variable which is a product of n times m, and it's this function. So if your n is equal to a times b, then this equal to a logarithm of a times b, which means it's a log of a plus log of b. Okay? It's a single function of a single variable, right? It's a number, and this is a number, and this is a number, right? A real number, okay? All are real numbers. Not necessarily integer. What is half bit? How would you feel what is half bit, what it gives you? How much information? What does it mean I get information which is half a bit? 1 bit shrink your information twice, okay? N bits shrink your information 2 in the power n times. Half bit shrinks your information 2 in the power 1/2, namely square root times, okay? So it's just as well works on non-integer numbers here, right? It's just how much you had your initial uncertainty, how much you shrunk it. 2 in the power number of bits. Could be non-integer, right? So at the moment you think about, of course, mathematicians do funny things. They do all this, Dedekind sequences, monotonicity, etc. So they start from integer, and then you go to rationals, and then you use monotonicity. It's a beautiful mathematics by which you can define it for any number, rational, irrational. But it's as intuitive as one gets. It just shrink. Okay. So now let's come to letters. How much information that brings in this spirit? How much of, not that you are happy to somebody loves you, but in this sense, how much information the four-letter word brings? How many letters we have? In the English alphabet, we have 26. Okay? So what does it mean? This is a choice out of 26. So in a sense, you say A, B, Z, and you choose L. On the second position, again, you have, and you choose O. Right? How much information you get choosing out of 26? Logarithm of 26. So this word brings you 4 times log 2 of 26, which is 4.7 bits approximately, right? From now on, we'll be treating everything the same. Letters, proteins, DNAs, whatever. Just would be, you'll be asking what choice we make out of how many objects, okay? That's a simple idea of information. Now it's called kind of Shannon information. Of course, this is Boltzmann entropy. Now we ask a little bit more sophisticated question. We say we get a very, very long text. How, on average, much information we get per letter? Well, now when we look at a very long text, there are different frequencies of letters in it, right? And we can look at it and we can see it. So now we know numbers which are called pi, and I runs from 1 to n, and this is the relative frequency, so we define the probability distribution. We say that sum of pi is equal to unity. We know this. Every time you know something in advance, information that you get will be less, because you already know something, right? So the moment that you get this text, so you ask now, if you have a very, very long text, how much information you get per letter. So what you know is that in this very long text, the letter A would happen P1 n times. Okay? The letter Z would happen P26 n times. So we know how many times. What we don't know, what message brings. What message? The message is just a sequence of letters. So we find out that A is in the position 4, in the position 25, in the position 40. It brings us order. Okay? We know how many A's are there. We know how many B's. We now need to know in which positions they stayed, or in which order they appear. So now our information would be a logarithm of a total number of orders, or of choices. Okay? So what we now need to do, we need to ask how many ways to choose our letters out of these any letters, right? So now what you'll find out is, let me use the same notation, okay? So a total, as we yesterday already, and of course you know this formula, this is your total number of permutations of your all letters. But you know that the first letter would happen P1 n factorial, right? Well, you can put it this way. Then P2 n factorial, Pn n factorial. That's a total number of different choices or different sequences, if you wish, right? Now you take log of it, right? And this would be your information that you obtained out of it. And now, of course, I'll use a Stirling formula. So I say that when n is very large, that the logarithm of n is n log n, right? So now, when I write this logarithm in the limit of large n, using Stirling formula, I get n log n minus, this would come out of here, minus the sum over I from 1 to n, n pi log n pi, and you get n log n cancel out. So what you've got, your information is minus n sum over I pi log pi. So now, if you ask what is your information per letter, this is Gibbs entropy. It's a minus pi log pi. If you want it in bits, will be 2 here. Sometimes people use nuts, then they use ln, natural logarithm. But this is essentially let you to see that the difference what the physicists used to think between microcanonical, namely we have n states and they all have equal probability, and then our degree of uncertainty, now speaking, as a logarithm n. If we know that we have different states and they have different probabilities, that's our degree of uncertainty. Any message removes this uncertainty, and then he brings information which is this uncertainty. Okay? So the idea which 20 years after Szilard clearly formulated Shannon is that information is a removal of uncertainty. You can use different measures of information. This is a very, very particular way. You know, information is a word of language. It's a very loaded word. It can mean many things. So this is a very, very specific way to define it. It's defined as a removal of uncertainty. So you count your uncertainty. In this case, again, as we say, it's a minus log of probability or logarithm of 1 over probability. For every letter I, our uncertainty or surprise is a logarithm of it. And this is a mean logarithm. This is a Gibbs entropy. Is that clear? It's a sheer triviality, and it's extremely powerful idea. The more trivial way you can reformulate your theory is the more powerful it is. Right? Every time somebody tells you it's paradox, it's not trivial, etc., it means that somebody does not really understand it. So you aren't ready to work with it. Make it trivial. So this is trivial, and now it's a very powerful idea. Okay? So now, you can actually use it without any probability if, again, you use the same idea of your box and your compartment. So you can just imagine that now in every box there are a different number of compartments. This is so important that I'll give you 2 different ways to see this Gibbs formula. So this is M1 compartments, but this has M2 compartments, and they are generally Mi compartments in the box number I. Okay? Well, just imagine this. Okay? So now you want to know, and you can define that for every box there is a pi which is mi divided by the sum of I from 1 to n mi's. Okay? And you also call it mi over m. So m is your total number of compartments. Okay? So now you ask, if somebody told me in which compartment my candy is, then I get the information which is log of m. That's a choice of that many compartments, right? But this information must be a sum, again, in the same simple spirit which we used before, but just it's something that takes account that you have a different number of compartments. So this will be a sum of the information about a box. There are n boxes, right? And plus the information about compartments, which is sum of about every compartment you get log of mi, and you sum over all compartments. Okay? So what is said here is that the information about a compartment is again information about a box, then information about on which compartment you get inside the box. Now, out of this formula, you find out that your I of n, the information about a box, okay, it's log m minus sum of pi log mi, and then you find out that this is minus sum of pi log pi. You just account that m is the sum of mi's, right? So that's what you get. P log p. Okay? So again, this formula which tells you, yes? Speak louder. Don't we have a mic? Mm-hmm.
Trying to understand the example. So if we know about which box is the candy in, so why do we care about the summation of the other box compartments?
No. What I'm saying is that information about a compartment is an information about a box plus information about which compartment inside a given box, right? So, but now I am asking what is the information on average about a box, because different boxes bring different information. When I assume that, when I write this formula, that this is the I of m, I assume that my compartments are chosen totally independently. Each compartment could be chosen with the same chance. That's my initial uncertainty about compartment. Then I am asking, what is my initial uncertainty about a box? Okay? And my initial uncertainty about the box is this. It depends on how many compartments in it. Okay? I'm just giving you the same formula, but instead of probability of choosing this letter, I'm telling you this is how many compartments it have inside it. It's just to give you a different intuition. Okay?
So why is that formula for pi not 1 upon mi? I mean, why does it depend upon all the compartments?
It depends on all the compartments because imagine that you have a letter with a pj equal to unity. What is the uncertainty of this box? No uncertainty. With a probability 1, you get this letter. What does it mean? All the compartments are in this letter, because your pi is mi divided by the whole sum, right? So if you choose your compartments uniformly and all the compartments in one letter, this letter brings no surprise. If probability is close to unity, it's a very little surprise. Most of the compartments inside this box, so with the overwhelming probability. Now, if there is a very few compartments, but again, it depends, of course, of the rest, how many compartments in other boxes. Okay? I see. You see, for different people, different things are with different intuition. Forget about compartments. Think about probabilities. Then it will be easier for you. For some people don't like probabilities. Probability tells you if something is has some probability, degree of surprise of it is a logarithm of 1 over probability. The less probable, the larger is the degree of surprise. Okay? What is the information? It's an average degree of surprise. That's it. Okay? Forget about compartments. This is just, for different people, different intuition. Okay. So, yes, questions? Take a mic. What? So what's the problem?
So I was asking, instead of breaking the information into a function of n and then subsequently into m, is there a, what would this look like if we just asked how in which compartment it is? Doesn't matter which box?
This is information. If you get answer of which compartment, that much information you obtain. You have m compartments, that much information you obtain. Okay? But you can obtain this information in 2 steps.
Yeah. My question was, what would be the method to get it in one go?
Huh?
What would be the method to do this in one go? As in, just ask which compartment it is.
That's, I'm asking, what was your uncertainty about the compartments?
Yes.
Is the logarithm of the number of compartments.
Yes.
It's as simple as this, okay? Now, what is your uncertainty about a box? Well, it depends how many compartments are in the box, right?
Yeah.
Because some boxes have much less uncertainty. The box which has most of the compartments have very little uncertainty, right?
Yes.
It's a very high probability that I get this box, okay?
Yes.
So again, we're talking about extremely trivial mathematical notions. What is really important here is to get your own intuition. So that I will be asking some question, you will immediately answer, and at least 20% your answer would be correct, okay? And so this intuition very much personal. It depends on what kind of intuition you like to have. You may think, well, I know a great statistician, a friend of mine, who always uses surprise. He doesn't like uncertainty, okay? And he several times demonstrated me a very brilliant way to understand something, but he always used the word surprise. He said, my surprise, your surprise, I'm more surprised, I'm less surprised. Okay, so other people, but what I found teaching this course, for like 20 years, is that some people don't like probability intuitively. I mean, you need to know it, I mean, you're a physicist. But compartments help to these people, right? So they think about like, all compartments are the same, but this box just has more compartments, right? It's the same as saying it has more probability. More questions? Yes.
How do you get write this last expression minus summation pi log k? In putting the value of log of m, you have got this last.
Yeah, this minus this is equal to this. That's what I was saying. No, check it. Yeah.
So you have put the value of, so how are you getting it mathematically? This I'm not getting the final expression.
Yeah. That's the definition of m. It's a sum over m's, right? But the sum over pi's is unity. Okay? So you can just, well, mi is m times pi. Okay? Now, log m cancels log m. Okay? Thank you for this question. I mean, every time you don't really see how I did it, ask me, because I won't derive most of the formulas because they are in the book and you can open the book and see all the derivations with all the details. But sometimes if I do derivation and you don't follow it, ask me, okay? It's really important that you follow a trivial step. Okay? Good. So now we understand that all that what Gibbs and, and Boltzmann taught us was essentially a simple choice. And what we're actually counting, I remember the first time I gave this course at Weizmann at my institute, and we have this kind of culture that not only, it's a graduate school, we don't have undergraduate students, so I'll teach. It's usually, I mean, very often professors come to lectures of other professors, and when I first time taught is that another professor, Codex, he is a very famous brain researcher, and discovered something about memory. He, after the second lecture, I guess, came to me very shocked. And he asked me, are you telling me that the entropy is not a property of a physical system? And I said to him, yes. This is the main message of Maxwell, Szilard, that entropy is not a property of a physical system. It's about us and this physical system. It's our degree of uncertainty about this physical system. And then he asked me, totally shocked. So the second law of thermodynamics is not a law of nature. And the answer is yes. It's a law of our relationship to nature. This is very important to understand, which means that what I'm telling you mathematically is totally trivial, but conceptually is very important, right? Okay, good. So now let's go forward. And now, okay, let me do a thing which is, again, something which physicists very well know, but in a different way. So somebody gives you a sequence of letters. And 1 million words like this. That's Hebrew. That's in Hebrew very famous. It's the beginning of the Bible in the original. All the rest are translations. Okay? So now somebody gives it to you. This is one sequence of letters. Like, you know, information theorists like to call it string. So you have a string, very long. And ask you the question, how probable it is. It's blatantly self-referential. No ensemble. You aren't given an ensemble. You say, okay, here is your ensemble, here is your thing. Okay, so just look in the ensemble, how many times it happens. No ensemble, just one text. Well, this Western civilization is built on this text, so it's really important. It's a singular text, right? And then you ask how probable it is, and then you know that in amount of information in the Shannon cells would be just a logarithm of 1 over probability. How would you answer this question? Well, first of all, is it answerable? What's your intuitive answer? Because if I'm asking, then it's probably it has an answer, right? Why would I waste your time? Yes?
Yeah, so in the entire list of letters you're given, you find out if it has n, if it's a sequence of n letters.
It's 20 letters. You find out that there are only 20 different letters.
Okay.
It's a first alphabet, by the way, in history, and it's smaller than most of the other alphabets. It does not have vowels. So there are 20 letters, okay.
Yeah, so in these 20 letters, you find for each letter how many times it occurs in that sequence. And then you do that becomes the PI when you divide over 20, and then you do a summation. PI
Exactly,
log.
exactly. Thank you very much. You can do it in a little bit, where's my, you can do it in a little bit more kind of detailed way. Of course, you can immediately jump, but I really want, let's do it a little bit slower and concentrate on every step, because it's essentially all stat physics is here. Well, first of all, we use a trick which we'll be using over and over, and I want you to see it explicitly, and this trick is adding numbers. So what we do know, and I mean, there are people here who know large deviation theory with all bells and whistles, but the simplest part of it, if you add random numbers, and these random numbers, whatever is their statistics, are independent on each other. Namely, you choose every number independently. Then what you know, the first statement is the simplest part. It's called law of large numbers. That it approaches its mean value, the sum of these numbers divided by the number of numbers, exponentially fast. Then you can ask what are the probability of it being not exactly its mean value, and you have a central limit theorem which says this probability is Gaussian. And then you ask, okay, but what is the probability of even larger fluctuation? And that's your large deviation theory. So there are like concentric statements, but we'll be using only simple things. So, but we're interested in the probability of a sequence y1, y2. This is my letters of my alphabet. This is Aleph, this is Bet, whatever. yn, this is the total number of words, of letters in the Bible. So I'm interested in this particular sequence of huge N letters, and I want to have independent numbers to sum. So at the first step, and then we make a second step, maybe today, maybe tomorrow, I assume that those letters were chosen independently, and so I know then if the probabilities, if they were independent, probabilities were multiplied, and the logarithm of probability would be summed. So I take a log of it, and I say that this is the sum from 1 to n of log p of yi. Well, but there is only 20 letters. N is 20, right? So it's really, because they are independent, what I really need to be summing is the probability of a given letter and this letter. So I can just as well say that this is the sum of j up to n p of yj. Right? So this is a position in the sequence, and this is which letter of the alphabet I am using, right? And, sorry, logs. But a mean log is entropy. N. Okay? So now what I obtain the following statement. This probability of a given sequence of n letters is an exponent minus ns of y. This is the probability, this is entropy of my language, of my alphabet. It has no relation to this sequence, which means that all sequences have the same probability. Sometimes it's formulated let me write it as a mathematician. Almost all events are almost equally probable. That's what we physicists call microcanonical distribution, and information theorists call asymptotic equipartition. It's the same statement.
probability will depend on the length of the sequence.
Yes, it depends.
So it changes with length, but
Yes,
for a fixed
exponentially decays with n, and entropy is the rate of decay. So I really want you now to start seeing entropy as large deviation people do for living. Entropy is the rate of exponential decay of your probability or exponential growth of your number of possibilities. That's why entropy is a logarithm, right? Okay? So what we really assume doing your algorithm, we did a very important assumption. We assume that our sequence is typical. Tomorrow we'll return to it armed by relative entropy, and we ask how wrong could we be making this assumption. Okay? But what essentially it tells us that if you have a sufficiently long sequence, the longer it is, law of large numbers tells us, the closer it's to the true mean value and mean value of a logarithm of probability, then we can get probability taking exponent of this log, right? And now it tells us the same that we learned just 20 minutes ago, that the mean information out of a sequence per letter, it's a Gibbs entropy, because it's a logarithm of a total number of probabilities. And then we start feeling that there is something idiotically wrong about our alphabet. So let's take 26 letters, add to it space, exclamation mark, all this. So let's have 32 symbols. Okay? Well, generally, huh? Well, here, P of yj. No, it's a sum of logarithms from 1 to n. Yeah, each taken with its own pj. Okay. So now, if we ask how many, and we now want to encode it, namely transfer the same thing, we are now in a computer, so we want our letters to be transferred by zeros and ones, by bits, binary digits. So the answer is how long we need a word for every letter. So we have 32 symbols. Apparently, if we just try to have 0 and 1, we can only send 2 objects, right? If we have 2-digit word, 0, 0, 0, 1, 1, 0, 1, 1, we have 4. Generally, if our word is m lengths, then 2 in the power m is the number of words in our alphabet. So we use 2 signs, 0 and 1, but we make a word which is 5, right? So this like 0, 0, 0, 0, 0. And 2 to 5 is 32, right? So if we just take binary digits, encode our English 26 letters plus space plus exclamation mark and all the other things, we would use 5-letter words. But Shannon, Gibbs, and other people tells us that if you take probabilities of English words, you know that the probability of E is 0.13, and the probability of Q is 10 minus something. So if now you sum pi log pi together with all the signs from 1 to 32, you would get the entropy of your alphabet. And it will be approximately 4.1 bits. No. What I'm saying is, imagine that you write something. You need not only letters, you also need a space, right? It makes it 27. But you also need a point. It makes it 28. You need a comma. It makes it 29. You add exclamation marks and make you 30. You add question mark, it makes it 31. And then you add a semicolon and make it 32. So your text uses 32 signs, letters. Okay? Now, if you would try to encode it in zeros and one, you would say that you need a 5-letter words, right? So your A would be this, your B would be 0001, this would be your B, okay, etc. 32. In this case, per every letter, you would use 5 bits. Okay? So if every letter is encoded by a word which is 5 bits long, then per letter you spend 5 bits. But Gibbs tells you that you only need 4.1 bits on average, right? So it's when you multiply it by gigabits per second in every cable, it's a huge waste. If we would take our alphabet plus all the signs and encode it each one by 5, that would be 5 minus 4.1 times Google bits of information. So that would be totally wrong to encode all letters by the words of the same length, right? Means that we will be spending 5 bits per letter, even though we need on average 4.1. What to do? What would you suggest to do? Because there's a trillions of dollars waste if we would do this. How you compress? Again, you need to send somebody a letter of love. But what you are supposed to send only zeros and ones, right? That's what computer does. So you do encoding. So they ask you how you encode L and O and V and E. You know who solved this problem first? A painter. Ever heard such name? Samuel Morse. Well, by his name you can guess that he was a Protestant from Boston. They all have these fancy biblical names. Again, we're already speaking for 45 minutes. And like every 45 minutes, I'll be telling you a story, and then we will get back to formulas. Samuel Morse was a painter, and a very famous painter, and a very popular painter. And so he was painting a painting somewhere down south, and he got a message. Somebody took a horse and rode all the way from Boston to, I guess, Virginia, if I'm not mistaken, and brought him a message that his wife is very ill. So Samuel mounted a horse and rode all the way back. I don't know if you, I drove it several times. It takes like six hours of driving. So he rode the horse back home, and he was late. She died before he arrived. And he was so devastated that he spent the rest of his life, very successfully again, he was absolutely genius, saying that nobody would ever experience this because we need an efficient method of long-range communications. And of course, electricity and magnetism already existed. And of course, many people were trying to invent telegraph. He was invented telegraph, right? And Ampere, Weber, Gauss, I mean, geniuses. They all did totally unpractical. That's what geniuses usually do, unless they are practical geniuses. And what Morse invented, first of all, he had a very good engineer to help him. But of course, he was a genius in the sense that he understood that apart from technicalities, and technicalities are important, he invented this thing, right? Which meant his alphabet was essentially 0 or 1. Well, there were actually 3 things because there was a dot, space, and emptiness, right? So you can, but essentially it was like this, right? So you can dot, and so you can short signal, long signal. If you think, and history is very interesting, if you think what geniuses, I mean really great physicists did, they tried to use a needle, so you make a stronger current, it make a stronger magnetic field, it turns your needle like this, you call it A. If you took stronger current, you call it B. If you even stronger current, call it C. It was totally unpractical, right? So first of all, he really understood that to convey 32 symbols, you don't need 32 other symbols. You need 2 other symbols. But now how you solve this problem that some symbols are more frequent than others. So symbols which are frequent, you want to encode them short. Then your whole sequence would be shorter, okay? And how he first learned which letters are longer, more probable and which are less? Well, what Shannon did, and he already had the first computers, you just go, you open your telephone book, and you just count how many A's, how many B's. But Morse was a genius. So what he did? He went to a typography, people were printing, right? And he asked how often you order new letters. And say, we order letter E with more frequent than the letter Q, because they're just, used more frequently. And then he designed this E was a dot, okay? And Q was 5 symbols. So you use variable length code. Some frequent objects you encode by 1 symbol, and some not frequent by 7 symbols. So on average, your length of the word would be 4.1 and not 5, like here, okay? So you see, this is not integer, so apparently it must come as an average length of the word in your bits, right? Because this is the number of bits per object, right? Let's do our own design. Okay, so intermission is over, we're back to formulas, right? But it's a nice story about Morse, right? So let's do it ourselves. Let's design a variable length code and see how it's done. Because, of course, nature does it all the time, right? So what we'll do, we consider, incidentally, I want to ask you, I can use biological example, economics example, linguistics, or more physical. Would you have any preference, or you just want me to use all the things?
All of them.
All of them, okay, good. But I'm trying to be panoramic, so, but I think that you're smart enough that you'll be, okay, so this is a really important sentence, but it's called at the beginning. It starts at the beginning. The God created earth and heaven. Okay. Bereshit. Web. Okay. I guess it's just died on me. Okay. So on the rest, I'm on my own. So imagine that you have 4 and I guess C. So you have 4 bases. I'm now doing genetics. Okay. So as you probably know, all our DNA is just encoded by 4 letters. Okay. And so I have, let's say, an imaginal bacteria, or I don't know, a creature which has this appearing with a probability 1/2. This is apparently with probability 1/4. This appearing with probability 1/8, and this appearing with probability 1/8. Okay? So now I have 4 different objects, and I want to encode them by zeros and ones. Okay? So what is the length of word in bits? I need to choose that I have 4 such words. Okay? Well, the simple idea could be that you just need to choose 2-letter words. So if you say encode this by 0, 0, 0, 1, 1, 0, 1, 1. That's an encoding. Let's call it called C1. Okay? How many bits per object we use? 2. Okay? Good. But what is the true entropy of this probability distribution? This is a probability distribution, right? So let's compute its entropy, right? So let's take 1/2 log 2 plus 1/4 log 4, right? I'm doing minus p log pi sum, okay? And all my logs would be 2, right? Plus this would be 1/8 log 8 twice. Okay? Well, that's easy. This is 1, this is 1/2, this is 2, this is 1, and this is 3, right? So I would get 1/2 plus, oh, no, this is 1/4. Okay? So this is 2 plus another 1/2. And this would give me 3/4. 7/4. It's less than 2, right? So this encoding would have an average 2 bits per letter, but I need 7/4 bits per letter, which is less in huge encodings. And you know, and I am a bacteria, which means that it's metabolically costly to do encode, because I encode proteins, right? And so what I really need to do is to do variable length encoding. How would you suggest to go about it?
So we can choose A.
First of all, this must be the shortest. It's very often. Let's call it 1, encoded by a single 6. Okay? Now, I can say, and what I'm doing is called Huffman codes. I say, treat this and this as 2 different possibilities. So I want to distinguish between this and all of this, which is also have 1/2 probability. Okay? So I would call all of it 0. Right? 0, 0, 0. Okay? So on the position in which it stands 1 here, it would stand 0 here. Right? So that every time I see the first position 1, I know it's this. Now, when I say 0, I know that it's one of this. Is that clear? Good. Now I need to distinguish inside this formula, right? So now what I'm saying, again, let's treat this and this as 2 different entities, okay? And I say that this would be 0 and this is 0, okay? So if in the second position I see unity, I know that this is this. So 0, 1 means that it's this. Now 0, 0 means that it's one of those. And to distinguish between these ones, I need to say that I distinguish this, right? It's a clear algorithmic way of building a code, right? You can also start from it's like a tree, right? Those my branches, or you can start from a stem, or you can start from a branches, but you say that you start from most probable, and you combine everything else, you distinguish between them, then you go along this branch, you distinguish between them, then you go along this branch, you distinguish between them. That's your variable length code, which means that sometimes you need 1, sometimes you need 2, and sometimes you need 3. What is the average code length? Well, you use 1 with a probability 1/2 plus you use 2 with a probability 1/4. I am computing mean length or code word length if you wish, okay? And now I have 3 with a probability 1/4. Which is exactly the entropy of my probability distribution. Okay? So this is essentially, and now speaking of a real thing. So in a real nature, we have 4 these things, but they are themselves used to encode proteins. Right? So now, first of all, this is clear? Yes.
So if I count all the bits for these 4 letters, then we are getting 8 bits for code 1, but we are having 9 bits. In total, we are having 9 bits. So doesn't it...
What do you mean? There is 1 bit, there is 2 bits, there is 3 bits.
Yeah, if I add all of them, then it turns out...
What do you mean you add all of them? You don't add all of them. You compute average.
Yeah, let's say if I have to send a message AGTC, then the number of bits I need is 9, isn't it?
If you send a message which is AGTC, then the number of bits will be 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah, but in code 1, it's just 8 bits. If I look at the code 1, so it is shorter.
Absolutely. If you send a message which is these letters with equal probabilities, this is the way to go. But if you're sending this with these probabilities, this is the way to go. That's it. Your way to encoding depends on your probability. This is your PIs, right? So your way of encoding depends on your probability distribution. If you have uniform probability, microcanonical, you use uniform encoding, right? If you use, because you are not interested in sending a message AGTC. You are interested in sending 10 to 23, right? Things. And then you ask how much metabolism I need to do for it. Because every time you do this, you burn your ATF molecule, right? Okay? Yes, take a mic.
Yeah. To denote letter G, why can't we just use 1 bit, I mean only 0? Why do we need 0 and 1? To denote the letter G in the...
Good question. If you always lose, that's what in quantum information people always like this example. Let's just have an alphabet of 1 symbol. Then there is 0 information, right? Just by definition. So there is no choice, right? You use only 1 symbol, and that means that you don't have any choice. You need minimum is 2 symbols. Then you can use words of different, because 1 in the power m is still 1, right? So how many words you have? 1, right? But if you, well, m words. But if you have binary, then 2 in the power m is very much growing function of m, right? So you can that many words of your language if you use 2, or you have 26 in the power m. This is your English language.
So to represent A, you just used 1 word, 1 letter, 1. To represent A, you used 1. G, to represent G, you are using 2 letters, and to represent T and C, you are using 3 bits. Now I'm wondering, why do you have to choose G to have 2 letters? You could have only 1 letter, right? A is 1, G is 0, T is 0, 1, C is 0, 0. Why do we need extra?
What do you mean?
Uh,
Yeah, but well, okay, there is one point. Maybe that what you mean is the following thing: that an important question here is now I have a string of zeros and ones, 0, 0, 1, 1, 1, 2, 2, 2, and I need to know where the word starts, because maybe I need a comma, which would be an extra spend, right? So what you really ask, is it okay, for example, I write, again, let's use it, A, G, T, C, I write it, and I have 0, 0, 1, then 0, 0, 1, then 0, 0, 0, right? So I have this sequence. How do I know where the word starts? And that's precisely, this is the question which is called prefix-free code. So now, what you find out, that you really need all your words to start from 0, right? And so every time you know that you hit 1, you are at the end of the word, okay? That's why you need this. And then again, you may ask, maybe it's not optimal. It is optimal because it's 7/4. And this is 7/4, okay? So this is how you actually reach this limit. Okay, good. But that's not the end of linguistics. It's just the beginning. And of course, I'm doing not only linguistics, but many other things. What I started to ask is how many things these 4 bases are actually encode. They encode amino acids. Okay? You know how many amino acids are? 20. Good. So you have 20 objects, right? You have 20 objects, and you have m equal to 4, namely, well, n, sorry. So n equal to 4, so your alphabet has 4 letters. How long a word you need to use? So your word is M. You have 4 letters. That's how many words you would have if M is the length of the word. If M is 1, you have 4 words. If M is 2, you have 2 letters, right? For example, you use AG, AT, then you have 16, and it's not enough for 20. So you need to use M equal to 3, and it's called triplet code, right? Is, by the way, physicist George Gamow who predicted that nature must use triplet code, right? And then what you find out, that there are how many 4 in the power 3 is 64. But you have only 20 amino acids. So you have a redundancy. You have 60 words and 20 objects. How nature uses it? Some amino acids are encoded by the same sequences of bases.
What is 20 you are saying?
There are 20 amino acids. Our proteins consist of amino acids. Okay? They need to be synthesized. Okay? And for this, you need to encode on DNA. DNA consists of these 4 bases. There is nothing else. 4 letters in this alphabet. In the most important alphabet of life, there are 4 letters. And so we now understand that you need to every amino acid must be 3 letters. So one amino acid would be A, another amino acid would be A, G, A, etc. Okay? But then you realize that there are 64 such words and only 20 amino acids. And this is the first time we meet something which is very important, and I even write this letter over here, and it's called redundancy. And this will be our next subject. Redundancy means that you have more expression, and so some amino acid you encode by different sequences. And usually, and nature is so smart, well, actually learned it hard way, that the most frequently used amino acid you encode by many different ways, and they are usually different only in one base. That means that you protect yourself against errors. So if, for example, these two encode the same amino acid, then any error of changing this would be irrelevant, right? That tells you this important idea that you use redundancy for protection, okay? Now, let's go forward. Oh, I already erased this Bereshit. Anyway, so let's now look at our sequence and ask the following thing. Yeah, maybe, you know, maybe before I just, in view of this other beautiful lecture by, about quantum information yesterday, I was somehow a little kind of, well, I'm giving you everything is very, very empirical, physical way. I now want to make a mathematical statement just so that you would understand that what is behind all this is actually very beautiful mathematics and very, very rigorous and sophisticated. So again, the most important formula which appeared so far, it is this. The Gibbs entropy, right? S of P. You can actually show that if you have S of P1, Pn, and you ask it to satisfy so just formally say, I'm looking for a function of n numbers for any n. I impose a condition, the sum of a pi from 1 to n is equal to unity. I want this function to be continuous, monotonous, and I want it to satisfy this recursion relation. For example, here is the entropy of probability just between 1 and 2, right? If I know that either 1 or 2 happened, then this is the probability of 1 happening, this is the probability of 2 happening, right? And this is the entropy of this distribution. Okay? And this is the entropy of a distribution where just 1 and 2 is indistinguishable, right? It's like I built Huffman code. And it's a very beautiful theorem, and an unbelievable beautiful branch of mathematics which comes out of it is to show that the only such function is this, P log P. Okay? Again, it stresses this recursive character of obtaining information, right? You say this or this, right? Like if you have a road and you have a fork, you ask which way to go. Okay, you need to go this way. Then you ask which way to go. You go this way. And eventually you come to your destination and you ask how much information I need to come to this destination after m forks, right? And then again, because at every fork it's just 2, then you have log m bits. But if you would drive in a city where there are 3 waves out of it, then it would be log 3 of it, right? So it's always dividing into first choosing whether 1 or 2 happened and then distinguishing between them. So this is really a mathematical statement. Even though we got it kind of empirically, but this is a general formulation. Okay? Questions?
So why do we need that this?
Huh?
Why did we need this algorithm? I didn't get it. So you wrote this.
This general formula tells you that this formula minus p log p is a only function which satisfies this recursive relation. Okay? It somehow tells you that there are no other measures of it. Because in a sense, people can say, when you start talking about quantum mechanics, and I also give you a little bit of quantum information theory, you have, I need to quantify uncertainty. Well, Heisenberg quantified to you uncertainty. It's an, you know, a mean variance of momentum times mean variance of coordinate larger or equal than h bar. But it's not the way quantum uncertainty is understood in the modern information theory. All modern information theory is about logarithms. Okay? This is very important. So you can use different measures, but they have very different mathematical properties. And that what we learn tomorrow is that when you have a Gaussian distribution, then variance completely determines Gaussian distribution. And Heisenberg used to work with a free quantum particle which has a Gaussian distribution, which actually extremizes the uncertainty. Then you can formulate everything in terms of variances. But for any distribution, the measure of uncertainty is log. And it's a very beautiful mathematics which grows out of it. And there is, I taught this course at NYU 2 years ago, and after me was lecturing Misha Gromov. He's a very famous mathematician. And he was lecturing on isoperimetric inequalities. Because he's so famous, and it was just first lecture, so I decided that I would stay after my lecture and listen what are the isoperimetric inequalities, because he's, you know, great. I mean, you have a chance to listen to great mathematician and lecture for students as I can understand. And he came to the room and he wrote minus sum over I p log pi. And I asked him, this is entropy. He said, yeah, of course. This is entropy, and as you will see, there are many things, but maybe just to give you a feeling. What we wrote, when I'm saying is that the equilibrium is a maximum of entropy in the given energy, or it's a minimum of energy in the given entropy, instead of this, I can tell you, a circle has a maximal area for a given perimeter or a minimal perimeter for a given area. And then you can go into d-dimensional space and ask about this, and it's all about it. It's an unbelievably rich mathematics over there, right? I'm not pretending that I'm explaining to you. I'm just telling you that if you're a mathematically oriented person, this formula, Gromov says that he thinks that this is like, with Euler and other things, like one of the 10 most important formulas that people ever invented. Right? So it's a very, very, and I gave you this relation just to show you how you can get this formula out of a very, very abstract requirement. Yes?
I wanted to ask, is this recursive statement
No, Bayesian inference is a more narrow thing. It will come tomorrow. And I'll talk about Bayesian things in much detail. I think that, I mean, when I was a student, nobody taught us all this. And the statistical physics that I was taught was about paradoxes. And I remember how I hated it, because it's my feeling that if somebody talks about paradoxes, means that you're totally confused. Okay, and then later I've realized that this statistical physics is trivial. There are no paradoxes. The moment you start to telling it in information language, it's just banality, like Laplace said. It's a common sense in formulas. Okay, so now let's do a next step, because I really want you to show you a few formulas, not only. So now, when we do this sequence, I don't know, y1, yi, yn, you may go step further. You may ask, wait, but is this not only frequencies of different letters? There are only some letters appear more often after some other letters, right? So you may look and you can find that when you see Q, you always see U after it. Let me write it like this. What does notation means? It means conditional probability of Q being followed by U. As there are a few words which are some names in African languages which being written in English would be different, but generally English has this rule. Wow, you say. You see, letters aren't really independent. They are dependent. There is something, I mean, after T is very often follows H. Right? So now you would ask, that means that if I look at my very long typical sequence, I can read these frequencies. Just not a big deal, right? Now what I need to do, I need to write pairs, right? So what I would say that I have PIs, it's a probability of different letters, but I also have PIJs, which would be P of I followed by J. This is a matrix, that's a vector, okay? Now, this is a probability distribution. If I sum Pij over J, what I will get? Unity. Unity. Because some letter always follows I. If I sum over all possible letters, that of course is unity. But how this matrix and this vector are related? Do they independent? Immediately answer without thinking. Are this vector and this matrix are independent? No, yes. Who thinks yes? Good. So you think they are independent. So there are independent positions of it, etc. But then imagine that if you have just follow every letter, then some appear more often after this and some appear less often, right? So what you have a condition that the probability of being in a position I is the probability of being in a position J times the probability of come from, from J and I and Ij. So what are you saying? That to observe the letter J, I need to sum over all previous letters with the probability that J appears after this letter. Agree? It's called stationarity. What it tells me, how this vector and this matrix are related. Yes? This one. It's a, look, like Laplace said, it's a common sense expressed in formulas. It's a statement the following. Some letters always follow my letter. If I sum over all letters, then it will be, with the probability 1, some letter will appear after my letter. This is the statement. It's a sheer triviality. This is a probability that J follows after I. If I sum over all J, it will be unity. Some letter follows. It's a very long sequence, right? Okay?
But we need to sum over both I and J, right?
No! No! No matter what is the letter, I could be any letter. I sum over J, which means I'm saying that whatever letter I choose, some other letter would follow it. That's triviality. Look, you have a long text, okay? You say, okay, I want to pick up a letter K. What is the probability that some other letter follows K? Unity. Always, after every letter, there is some other letter. Okay? Still not clear? You look unhappy. Try to formulate what makes you unhappy.
Like, when we're talking about K here, you fixed K, right? So that's fine, like K will be followed by any letter.
Because it's an infinite sequence.
But choosing this K also had a probability, right? That we started looking at K.
No, it's a conditional probability. It's a probability conditioned on I. There is nothing about I here. What is the probability of I is not here. It would be only from this formula. Okay? It say if I have, that's the idea of conditional probability. If I see K, what will be the probability to see A after it? Okay? It's a probability with respect to J. And sum over J's is unity. Okay? That's the whole idea of conditional probability. Now you want to know what is the probability of I, you need to act by this matrix. So in a sense, what I find out, this P vector is P matrix times P vector. What is this formula? So what is the relation between this matrix and this vector? This is eigenvector of this matrix with eigenvalue 1. In the lecture 4, if we'll have time, I'll tell you how Google make $60 billion out of this formula, because this is essentially the heart of a Google PageRank algorithm and Fred-Gorham theorem which is behind it. So, but what we now say is that we now really need to think about our text in terms of probabilities of one letters following another.
So this equation that you have written, Pj equal to summation over I, Pi, J, Pi. So yeah, this. So does it means that we are trying with this, the probability of getting jth letter is equal to the conditional probability multiplied by the probability of getting ith letter. Does it mean this?
Yeah. You ask, what is the probability to see J? The answer is, look one step back. Took all possible letters, which could happen in the previous position, multiply by the transition probability. That would be a probability to see J in this position.
I runs from ith to 0.
I runs from 1 to n, to all possible letters. Okay? This is the first example of which we'll use over and over. It's called a chain rule, right? So what is the probability to have I times probability to pass from I to J? If you sum over all i's, that would give you probability of J, right? Okay? Which shows you that, of course, this is something which has more information than Pi, right? Because the moment you have a matrix, when we come to quantum information, that's the difference between pure state. Every quantum state is a vector in the Hilbert space. A density matrix is a matrix. It's something more, right? So now, if I would like to do this law of almost all events almost equally probable, I want to ask what is the probability of my sequence. I need to take probability of, well, let's take a log. So again, I want to know how to use a law of large numbers, namely to sum things. This is the last formula, and then I stop. So you say, take the first letter. Well, let me write this. So take the first letter, multiply by the probability of a second letter happening under the condition of a first, multiply by the probability of a next step, etc. Okay? It is called Markov process, which means that I do not account for three-letter correlation, etc. I'm only saying that the probability of seeing next letter completely determines but where I'm stand. This is probability which only depends on one previous thing. So if I take a log here, I would take a log of my first whatever it is, and I sum k over 2 up to n logarithm of probability of yk plus 1 yk. Now I have independent random numbers to sum. This would be totally irrelevant in the limit n going to infinity. And you find out that I would now need to compute entropy. It's again a mean logarithm. Average, everything. So if I want to really get it 1 over n, this 1 over n, this 1 over n, this would be an average thing. I expect it to be less, because as we thought that this, and that's where we start tomorrow morning, and we defined the most important notion in this course, which is called mutual information and then relative entropy. Okay? So we'll stop at this point. Questions?
Can you please clarify what?
Take a mic. Because I want everyone to
Yeah.
hear your question.
Yeah.
Right?
Can you please clarify once why the average code length should be equal to the entropy? Because that's the Hoffman coding is doing, right?
Yeah, it's think about bits. This is the simplest way to think in terms of bits. Okay, so you ask how many bits you need per your object, right? And then we computed it just by this combinatorial formula, because it was a choice of all orders. Okay, so it is that amount of information per object. Your objects could be, I don't know, cars. Okay, so you want to encode different cars by zeros and ones. You ask how many. I mean, you have cars on the road. Okay, and you're encoding them by 0 and 1. But some cars happen more often. Okay, so you use on average, you see how many bits you spend per car. That a word length in bits. Okay, because the confusion is because I was encoding letters by bits, but letters already letters, right? But I was asking how many my word was in bits. Okay. How many zeros and 1 I need to spend on average per object. An object could be a car, a protein, or amino acid, or whatever. More questions? Yes, take a mic.
Yeah, so I have my question is like from the very start of your lecture where you said like if you have n choices, typically you have to ask log n questions. Suppose like doesn't that answer to this like number of questions that you have to ask, it also depends on the strategy that you're using. Like for example, if my candy is can be in anywhere in the box, like n boxes, and if I have a strategy that I start from one from the leftmost box to and and start asking whether it is in the first box, whether it is in the second box, and so on, like a sequential manner, then
Yeah.
typically I would have to ask n, like order n questions.
Yeah.
Where if I were to ask questions
Yeah.
like whether the candy is on the left half
Yeah.
of the box,
Very,
like,
very good question.
like binary style,
Yeah.
then it would
Very
be
good
n.
question. So what you're saying is that we could be idiots and ask the wrong questions. Okay? So in my definition, and that's why I use a mathematically correct definition about this subdivision P1 and P2, because this is absolutely correct formulation. It's only one function, P log P, which satisfies it. But essentially it means what is the minimal number of questions that you need to ask. Because we could be as idiotic as we want, and we ask many, many questions, much more than we need. So the information is what is the minimal number of questions that we need to ask to totally eliminate the uncertainty. Okay? And that would be a Boltzmann entropy, and Gibbs entropy is what is on average minimal number of questions per object or minimal number of bits we need to specify on average. That would be Gibbs entropy or information. Or Gibbs entropy and Shannon information is the same things. P log P. Okay? Yes?
Another question regarding this equation that you have, where you the first one on the top, basically, where you have this one. So here you're saying that this summation going from 2 to n, 1 over n, that thing, that
Yeah.
is an average of log p, and all of those are equal. Is that what you said?
No, what I'm saying is that for a given sequence, right, I just have a given probabilities and I just compute them, etc. So what I really need over here, I need to sum over all these possible positions. Yeah? But the statement is that now it's like when you consider Ising model, you can think in terms of spins, but you can think in terms of bonds, right? So your bond is actually something which gives you Gibbs weight, is either exponent j or exponent minus j. So the same is here. This is a transition probability. So you're saying that what I really now need to count is all the probabilities of different transitions. And as I have a very, very long sequence, I would have all possible transitions. From A to B, from B to K, from T to H, I need to sum over all of them. Some of them would have zero probability, right? A Q is always follows by U and not by any other letters. But what is the statement is that when you be computing average logarithm, you will be now summing over all possible transition probabilities, okay? And that would give you a true probability in the asymptotic limit of large n. Yeah, we'll start tomorrow from this formula. Trust me, we haven't finished with it. We just started. This is now really non-trivial generalization of a Gibbs formula appears. Nothing much after it.
So my question is like regarding this only, like these LLMs that people have created, right? The large language models, like for example, ChatGPT, right? Are they always assume like Markov chain of the strings of letters? Is that?
Oh no, it works much more in a much more complicated way, but mostly, particularly all this kind of deep learning algorithms, they are generally one step. They are doing, I mean, this is not a letter, which means just a choice of food. It's an unbelievably long vector. There is many, many things here, right? So you are working in a very multidimensional space, but you're always doing one step. Namely, that you have vector in this space, and you ask, what is the probability that at the next level of my computation, it's a multi-level computation. What is the probability that this vector would change like this?
So essentially Markov.
So essentially they do Markov, but in a multidimensional space.
Yeah.
And the rules that they do is very interesting. If you're interested in AI, ask me at the last lecture, because the last lecture will be like everything else which I did not have time to talk. But it's a very non-trivial random walk, but it's a Markov type. Yeah. Okay. Okay, let's have a rest.